All right, so as you saw in the introductory video, when we are verifying identities, we are not trying to solve. It's a very different thing. Solving is trying to get the variable, the theta, isolated so we can tell what it's going to be equal to and what value makes the statement true. But remember, these are identities. And in an identity, all values of the theta are going to make this statement true. So what we have to think about here is we have to think about it as more of a proof. And with a proof, you have a given, and then you have what you need to solve, or excuse me, what you need to prove. The conclusion that you need to reach. And then you're going to go through a series of steps that show how you can go from the given to get to your conclusion. That's what we're doing here. We have two sides of an identity. One of these sides is going to start out as our given, and the other side is going to serve as our conclusion. And what we're trying to do here is rewrite the given statement, the given expression, using algebra and using trig identities until we get it into the same form as what our conclusion is. This is very much like what you were doing last lesson when you were asked to simplify identities. But now we have an idea of what we want to end up with. So when we were simplifying, we were going through the process of rewriting our expression in equivalent ways to try to get it into the simplest form we possibly could. But we had to decide what the simplest form was. When we're verifying identities, we are still trying to rewrite an expression, but now we know what we're trying to rewrite it as because we have the other side of the statement. So in this case, we are looking at secant squared of theta minus 1 over secant squared of theta being equivalent to sine squared of theta. And as he mentioned in the video that you just watched, our goal is usually, or not our goal, our first step is usually to identify which side looks more complicated and start with that side. So in this case, I would say our left side looks more complicated. So this side becomes our given, and this becomes the conclusion that we're trying to arrive at. Okay, so one of the things that the introductory video did not ask you to do, but I am going to expect, is that you actually take whichever side you've chosen as your given side, and you must write that side first. So just like in geometry, the very first thing you do is you state your given. So if we're deciding that this is the bigger side, this is our given, I need to rewrite that side first. And then I start going through the process of using algebra and using our trig identities to rewrite this expression in other equivalent forms until I finally get it into this expression. So we always want to keep this in mind as our end goal. All right, so what could we do first? Well, one possibility is to look at our trig identities and to notice that secant squared of theta minus 1 is equivalent to tangent squared theta. So we're going to replace secant squared theta minus 1 with tangent squared theta in the numerator. My denominator is going to stay the same at this point. I haven't changed that at all. So there's my first logical step toward trying to reach this conclusion. Okay, now the nice thing about doing this that is different than a geometric proof is that we do not have to write our reasons for every step. We just have to make logical steps that make sense. Okay, so what should we do next? Well, there really isn't any identity that deals with this fraction in particular. So I think I'm going to use the hint that he gave us in the introductory video. I'm going to change everything to what it's equivalent to in terms of sines and cosines. So our tangent squared of theta, if I use the quotient identity, is going to become sine squared theta over cosine squared theta. And then all of that is over secant squared theta, which I can rewrite as 1 over cosine squared theta. Now that might look a little messy at first, but it's actually quite helpful because now we can think of our fractions as division problems. So we can think of this as sine squared of theta over cosine squared of theta being divided by 1 over cosine squared of theta. And we should all know that dividing by a fraction is the same as multiplying by the reciprocal. So I can rewrite this as sine squared theta over cosine squared theta multiplied by a cosine squared theta over 1. And now I hope it's fairly obvious that we have common factors here that we can cancel. And if I have sine squared theta over 1, then what I'm left with is sine squared theta, which was exactly what I was shooting for. So, since I have reached my conclusion, then the second expectation in terms of the form of these is that I want you to write QED when you think you're at the end. QED comes from a Latin phrase, but it basically means that you have it verified. You have come to its logical conclusion. You have verified this identity in this case, and I want to see QED at the end of your problem when you think you have all of the steps worked out. Okay, so 2 important things here to remember, because I'm going to consider this when I do points on your quizzes and tests. We always start by writing our given, which is just whichever side we've chosen to be more complicated. Always rewrite that first. Go through your series of logical mathematical steps, and when you get to your conclusion, always put QED as an indication that you are finished and that you have all of the steps worked out. Okay? Now, one of the benefits for some people and one of the disadvantages for other people when we talk about verifying identities is that there is oftentimes more than one way to get from our given to our conclusion. So this was one possibility that we could have done, but let me show you a second possibility of how this could have worked out. So we're still using the same problem. We want to verify secant squared theta minus 1 over secant squared theta. Whoops, I forgot the rest of that problem. Hang on a second. Let me fix that. Being equal to the sine squared of theta. Okay, so it's the same statement that we're trying to verify, and I'm still interested in starting with this side because it is still the more complicated side. So that's going to be my given, and I'm going to rewrite that, secant squared theta minus 1 over secant squared theta. Okay, but here's another way we could have approached this. Because I have two terms that are being subtracted in my numerator, and that's over a single term in my denominator, I can split the numerator as long as each term goes over the denominator. So I can do secant squared over secant squared, and then I can subtract a 1 over secant squared. Now, if that seems a little strange to you at the moment, think about what would happen if I had this and asked you to combine it. We would take the secant squared minus the 1, because I already have a common denominator, and then I would keep that as the denominator. So if I were combining this into a single term, it would end up being this. So I'm just taking it back apart and going back this way. Okay, well, how does that help? Well, now we have a secant squared of theta over a secant squared of theta. Anytime we have a term over an equivalent term, we get 1. Now what about here? Can we simplify 1 over secant squared of theta? Take a look at your identities. Hopefully you realize that the reciprocal of secant squared is going to be cosecant squared. Sorry, yeah, the reciprocal, wasn't sure I said that right. Let me say it again. The reciprocal of secant squared, that's what we're saying when it's 1 over. The reciprocal of secant squared is cosine squared. Okay, so check your identities again. What is 1 minus cosine squared equal to? One minus cosine squared is just a slightly different version of the Pythagorean, and it would be equal to sine squared. And again, that's what we were looking for. And so we're done. So when you compare these two, here's our first example, and here's our second example. You notice the second example has slightly fewer steps to it. Okay? And that's okay. The more we can find the more efficient way to do things, the easier these are going to be and the less work you'll have to do. But there is nothing wrong with this set of steps. This is still logical, it is still step by step, and it still gets us to the conclusion we want to get to, just like this did. Okay? And so sometimes I refer to this as the highway method, getting there quickly. This is more the scenic route, getting there in a few more steps. But the fact is, our destination is the same either way. And so both are perfectly legitimate answers on how to verify this identity. So again, when you're talking with your friends about the problems and the answers and maybe comparing to see what the answer is, don't be surprised if you both have different steps and yet both of them are correct. And when it comes to your homework, when you do the practice for this lesson, if you have a particular process, a particular set of steps that you've used for your identity, and it does not match what you see on the answer key, go back over it, check it, but if you're convinced that what you have is correct, It probably is. If you want to make double sure, you could ask Mr. Fairking to take a look at it, or you could send me a screenshot of it and I can get back to you and let you know whether it's a legitimate verification or not. Okay, so keep that in mind. There's usually more than one way to do these, which is again why his advice in the introductory video about try something is really good advice. Because if you try something, chances are really good that something's going to click. If you do a step, maybe 2 steps, all of a sudden things fall into place and you see how you can finish out the problem. And if you don't, if you do a step, maybe 2 steps, and it doesn't look like you're getting any closer to what your conclusion should be, again, don't be afraid to go back and try something else. In that first attempt, you're at least figuring out what doesn't work so you can make a better approach on your second try. Okay, so don't be afraid to go back and try something else if your first try doesn't seem to be working. But just sitting there and trying to work it all out in your head from start to finish before you write a single thing down is going to make you crazy. So try something, write down your steps, and don't be afraid to go back and try something else if it doesn't work. All right, let's take a look at one more example. The other thing I like about the introductory video is his encouragement that the only real way to get good at verifying identities is to practice them a lot. Again, there are a lot of different ways to go about it. You're looking for identities that are going to fit. You're looking for algebra that will help you get an identity that's going to fit. And as far as what to look for and what to try based on the type of statement you're given, it's really just about practice, 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 practice. So we're going to practice one more together here, and then you'll get lots to practice in your practice worksheet. So this time we want to verify the statement that 1 minus the sine of alpha plus 1 over, oh, let me say that again. I think I said that incorrectly. Let's try again. 1 over 1 minus the sine of alpha plus 1 over 1 minus the sine of alpha is supposed to be equal to 2 secant squared of alpha. Okay, this is what we're trying to verify. So which side do we want to use as our given? Well, again, usually that's the more complicated side, and that certainly seems to be the left side in this case. So we're going to use this side as our given, and therefore it is the first thing we are going to write down. Oh, I think I miswrote this. I did. We need to make a little correction here. This one's supposed to be plus. So my first denominator is supposed to be 1 minus the sine of alpha. Here we want to have 1 plus the sine of alpha. So let me fix that up here too so that doesn't confuse us. Okay? All right, so now that we have the correct given statement, what's the first thing we want to do with this statement in an effort to get to our conclusion? Well, pretty much any time you start out with fractions or you deal with fractions in identity problems, we usually want to combine those fractions together into a single fraction. So we have to go back to what we know about adding fractions together. We know that in order to add fractions, we have to have a common denominator. So having 1 minus sine alpha in the first denominator and 1 plus sine alpha in the second denominator means that 1 minus sine alpha times 1 plus sine alpha is going to become our common denominator. Okay, so in my first fraction, if I already have 1 minus sine alpha, then what I need to multiply by is the 1 plus sine alpha. So taking that times the 1 that was in the numerator is just going to give me a 1 plus sine alpha. In my second fraction, I started with a 1 plus sine alpha. I need both 1 minus and 1 plus, so 1 minus sine alpha is what has to be multiplied by this time. And again, when I multiply that by 1, I'll just get 1 minus sine alpha. So now when I go to add these together and get my single fraction, adding my numerators, gives me 2, and then sine alphas cancel out because I have a positive and a negative. So I'm just going to end up with 2. All right, does that get me to this yet? Well, no, not quite. So what else can I do now? Well, I could go ahead and use a little bit of algebra and FOIL out the 1 minus sine alpha times the 1 plus sine alpha. And that's going to give me 1 minus sine squared alpha. Okay, well, still not quite to this point of getting 2 secant squared, but I'm getting closer because now my denominator is a version of the Pythagorean theorem. And so I can use the Pythagorean identity to change 1 minus sine squared theta into cosine squared theta. And this is going to lead me to my 2 secant squared. If you don't quite see that, it's because we're saying I have 2 times 1 over cosine squared. Okay, and 1 over cosine squared is the secant squared that I was looking for. So 2 secant squared, there's my conclusion. There's my final answer. So Q, E, D. I'm done. Okay, so you've now seen 3 different examples of how to verify an identity. The one in the introductory video, and then the 2 that we've done here together now. And in the last one, you saw that there was more than one way that you can go about these. There may be another way you could go about this one as well. This one just seemed the most obvious, the most highway version. But if you have another way of doing this that mathematically follows rules of algebra and rules of trigonometric identities, then go ahead and use it. That's fine. Okay, so it's time to practice on your own. You've got the 7.4 practice sheet that you should be working on. You have the answers that you can check yourself with. And if you have any questions on any of the steps that you see in the answer sheet, please just send me a screenshot, take a picture of your homework, send it to me, and ask a quick question about, is this okay? Are these steps okay? They're different than what you have, but I think this works. Does this look okay? And I'll try to get back to you as quickly as I can with an answer of, yep, that's fine, or no, and here's where the issue would be. And if you have any other questions about this homework, please find the resources to get your answers, including emailing me if you need to. Okay, we will see you next lesson.